So Lewis acids are the species which can accept electron pair, and Lewis bases are the species which can donate electron pair. Let's take this example. This proton are electron deficient, so it can accept electron pair, and this ammonia has lone pair of electron, so it can donate its electron pair. So this ammonia act as a Lewis base and this proton act as a Lewis acid. So when they react, a new bond formation occur. So Lewis bases are the species which are structurally same as Bronsted-Lowry bases. So in Bronsted-Lowry bases definition we studied they have available electron pair, a lone pair or electron pair in pi bond system. So in Bronsted-Lowry bases, we studied this example like hydroxyl having negative charge, this methanol having lone pair of electron, and ethylene has having a pi bond system. So same definition applies for Lewis bases and same example applies for Lewis bases. So these Bronsted-Lowry bases and Lewis bases they are structurally same. The only difference is your Bronsted-Lowry bases give electron pair only to proton, but Lewis bases give their electron pair to anything that is electron deficient. So it can be your proton or any other species which is electron deficient. Lewis acids are the species which are electron deficient and capable of accepting electron pair. So all Bronsted-Lowry acid are also Lewis acid, but the reverse is not true. Let's take example. So this water and this methanol, they are Bronsted-Lowry acid because they can donate their proton. But how they are Lewis acid? So water, when it react with base, base will abstract proton. Proton is electron deficient species. So electron deficient species we know they are Lewis acid. So when this electron deficient species react with base, it will give you this compound. And again in this example with methanol, when it react with base, base will abstract this proton. So it will give you a new compound which is this one, conjugated acid. You can see here all the Bronsted-Lowry acid are Lewis acid, but all Lewis acid are not Bronsted-Lowry acid. So now we study the example where Lewis acid are not Bronsted-Lowry acid. So this BF3 don't have any protons, so it is not Bronsted-Lowry acid, but it is electron deficient species. How it is electron deficient species? So we know boron has 5 electron its outer shell, and with 3 fluorine now it has 6 electron in its outer shell. So it need 2 more electron to complete its octet. So that is why BF3 can accept electron pair to complete its octet. So BF3 is Lewis acid. Same aluminum chloride is also Lewis acid because it is electron deficient species. So this is the comparison table. Bronsted-Lowry acid, in their definition we studied they are proton donor. The structure feature involves is proton. In this example you can see there are proton which they donate, so that is why they are Bronsted-Lowry acid. And Bronsted-Lowry bases we study they are proton acceptor. So structural feature involve lone pair of electron or pi bond system. So you can see they are having a negative charge and pi bond system. So they can accept proton. Lewis acid. Lewis acids are electron pair acceptor. So structure feature involves proton, unfilled valence shell, a partial positive charge. Like in last example we study BF3, aluminum chloride. Now you can see in acetic acid and water hydrochloric acid structure feature is proton because they are Bronsted-Lowry acid, but we studied that all Bronsted-Lowry acids are Lewis acid. And in Lewis base The definition is electron pair donor. So they have lone pair or pi bond system. So Lewis bases are same as Bronsted-Lowry bases because you can see the structure feature are same in both the class. Okay, so same example you can write in Lewis bases. So representation of Lewis acid base reaction. We know electron rich species react with electron poor species. Electron rich species are base and electron poor species are acid. So you have to show direction of arrow from base to acid. So this is the example. Your water is reacting with BF3. So a new bond formation occur. So Lewis base reaction, one single bond is formed and no bond is broken. So a Lewis acid is called an electron-phile. Electron-phile are electron-loving species, means they are electron deficient. That is why they are electron-loving, because they want electrons to become stable. And when Lewis bases react with electrophile other than proton, then they are called nucleophile. So Lewis bases are nucleophile only when they are reacting with other electron deficient species, not proton. Okay, so in this example you can see this is Lewis base because it has electron pair. So this electron rich species is reacting with Lewis acid which is electron deficient. So now you can see bromine is reacting with carbon, not proton. So this is nucleophile and this is electrophile, and you can see green color here which indicates a new bond is formed. Okay, similarly this is Lewis acid, ammonium chloride is Lewis acid, and this is Lewis base. So you have to show direction of arrow from base to acid, and again this green color show a new bond is formed. So now this is the question, find Lewis acid and base, electrophile and nucleophile. So I will do first example. Here you can see this species is having an electron pair, so you have to show the direction like that. Now this is electron pair, so this is base and this is nucleophile because it is reacting with electron deficient species which is other than proton. So this is electrophile and this is nucleophile, and there is formation of new single bond, so you have to show the product like that. Now you can do the second example very easily. So this is not always necessary that only you have to make a single bond without breakage of any other bond. For example, this cyclohexene, when it react with Lewis acid, this chlorines come out. Okay, because you have to correct the number of valence electron of this hydrogen. So in this example you can see cyclohexene double bond, this pi bond is reacting with this electron deficient species proton and forming a new single bond which you can see in green color, and other side you can see this carbocation is forming and this chlorine is coming out. Now we will study some application of Lewis acid base reaction. In this example you can see BF3 is electron deficient species. So you can see here the p orbital is empty. So that is why this is very unstable because it can react very fast with any other species. Okay, so to make it stable you put diethyl ether on this Lewis acid. Diethyl ether donate its lone pair of electron to p orbital, empty p orbital, and make a stable tetrahedral complex which we call it BF3 etherate solution. And you know in Friedel-Crafts alkylation and acylation, these are simply Lewis acid base reaction. So your acyl chloride, your this chlorine will go with this ammonium chloride and it will give you a acylium ion. Now this acylium ion will react with benzene to give this acyl product. So other example in Diels-Alder reaction, this is also based on Lewis acid and base reaction. So this is all about Lewis acid and bases. Thank you.